This is going to be just a short lesson on an infinite geometric series. So one thing I wanted to point out is you'll notice these are the 5 formulas that we have for our geometric and arithmetic sequences and series chapter. The formula you're going to see in this lesson is not within your list of formulas, but it is one that you're expected to know. So keep that in mind, but we're going to jump over to kind of this page that you see right here. This will be fairly brief, but the idea is simply this. If you take a look at the series playing out here, remember a series is a sum, which is why you're seeing the plus signs. But you'll notice within this series, at the end of it, you just see a ... meaning this is a series that goes on forever. There's no limit to it. We don't know what the ending, there's no term value. It's not saying find the sum of the first 4 terms. It's just saying find the sum. But how do you do that if it goes on forever? Technically, there is no exact sum that you could ever come up with for this. There is simply a value that you would be approaching. The more numbers you add, you're going to be closer and closer and closer to some value, though you would never actually get there. So I wanted to show you this page because this is a good graphic representation of how this works. So if we just said, let's just say find the sum of the first 2 terms. So right here you're seeing the sum of the first 2 terms is 0.75, and that's what they have graphed within the graph right here. So here's the sum of the first 2 terms is 0.75. If you were to take the first 3 terms and add those together, right, their sum would be 0.88. And so that's what you're seeing reflected right here with this. So the sum of the first 3 terms would give you the result of 0.88. And so that's that point that you're seeing on here. If you were to do the sum of the first 4 terms, this is what you would get. And so they plotted that on the graph. The sum of the first 5 terms is 0.97, and they plotted that on the graph. And if you kept on going, you would continue to see this arc flatten out and get closer and closer and closer to 1 as the answer, but you would never actually land on 1. You would forever get closer and closer to it. So 0.9999999, it would get closer to 1, but you'd never actually get to 1. What we've seen before in the past with this type of an idea is we call this an asymptote. It's like a boundary line. It's the line that you are approaching, but you would never actually land on that line. So what they do for the infinite geometric series is they identify the number that you are approaching. It wouldn't be the actual sum because you could never actually get to this number, but the more you add, the more of this series that we add on, I'm going to get closer and closer to 1, even though I would never actually get there. So they identify the sum as the number you are approaching. So we would say this series has a sum of 1, because we're going to be really close to 1. We just never would actually get to 1 as our answer. So that's the main idea behind this. So let me give you just a couple cases. Here is a formula that we're going to be using for this. Remember, this is not a formula in your formula packet, but it's one you're expected to know. Luckily, it's a very simple formula. It's the first term, so we might see this as a of 1 or u of 1, same thing. So this is the first term of the sequence divided by 1 minus the common ratio. So really simple little formula right here. First term over 1 minus r. There's a catch to this, and that's simply that in order for this to work, your common ratio has to be a number between positive and negative 1. That's essentially what this statement is saying right here. So if it's not a number between positive and negative 1, then this doesn't work. We would have to simply say that the sum does not exist. There would be no asymptote to that, and so there's no boundary line, and so you wouldn't be able to have a sum. So it's just something you got to look for. You probably wouldn't recognize it if you just threw numbers into the formula every time. You may not catch this. So it's something you got to pay attention to. So there's 2 ways that we can run into this scenario. Let me jump over to part B. This is the more likely scenario that you're going to run into, where you have a pattern, and then it's like that ... So I can see that this goes on forever. So that's how I would recognize it as infinite, is because it goes on forever. There's no specific number of terms here. this just goes on and on and on. So real simple, just two things I need to identify here. The first term, which is 1, so I'm going to put a 1 in for the first term, so that's the numerator, and then 1 minus the common ratio. Remember, the common ratio you can always find by taking any term and dividing it by its previous term. So if I took -3/4 and divided it by 1, I get my common ratio, which is -3/4. So if we put all that into our formula right here, here's the first term. I'm doing 1 minus the common ratio of -3/4. And if you clean all that up, this would be the answer. So this is the sum. If you saw this graphically, all you would see is that there is an asymptote at 4/7. So the results would be forever approaching 4/7. We'd never actually land on it, but the more numbers in this series you continue to add together, the closer to 4/7 you would get. And so we identify 4/7 as the sum. Do keep in mind, this only worked because my common ratio is a number between -1 and +1. So because it's a number between -1 and 1, that's why I was able to go ahead and say that this is my answer. If it's not a number between positive and -1, you simply have to say that the sum does not exist. There's no solution to that, so you can't do it. This is another way that we might run into this. This is unlikely for, a little more unlikely for like an IB test question, but let's just identify it so you can see it. But obviously with the infinity symbol right here, we would recognize this as an infinite geometric series, and so we know to go to this formula right here to deal with it. So a couple ways you can identify what the first term and the common ratio are. The easiest way is to simply understand that this models the geometric sequence formula. So right here should be sitting the first term. So 5 is the first term of the sequence. And right here is the common ratio. So 0.8 is the R value. And so that's just simply the easiest way to identify the numbers for the formula. Is just by recognizing the pattern that this is falling under, which is this pattern right here. If you weren't seeing that, or if we had something a little more unique, you could still figure out the first term. If I plug in a 1 for I, right, 1 minus 1 is 0. Anything to the 0 power is 1 times 5 is 5, and that would give me my first term of the sequence simply by plugging in a 1 for I, or N, or whatever letter is there. If I plugged in a 2, I would get my second term of the sequence, and if I do my second term divided by my first term, I could get my common ratio that way. So that works too. But anyway, once you've identified the first term and the common ratio, we just plug them in, and the rest is calculator work to get our answer. So remember that this works because 0.8 is a number between positive and -1, so that's why this works. So here's a case where, let me show you. Here's a case down here where this wouldn't work because if you look at the common ratio, 5/4 is a number that is larger than 1. So as soon as I saw this, I would have to look at this and say, okay, my common ratio is bigger than 1, so this is not going to work. So you'll notice even in the directions right here, it says if it exists. So this is a case where we wouldn't even have to do any math on. We would just say it does not exist because my common ratio is bigger than 1. So that's just something to always check for.